Orbital velocity is independent of not only that orbital velocity, and in the next class we can discuss that escape velocity also. That orbital velocity and escape velocity, they don't depend on mass of that satellite, they depend only on that mass of the planet only. So because why? Because here in this formula V0 is equal to square root of gm by r plus h, there is no provision for that small m, that is the mass of the satellite. Next we are coming to that geostationary satellite. Geostationary satellite means, in this case, this earth is here and this earth is rotating from west to east like this, and now here we are taking a planet as usual. This is the r, and again this planet is rotating, this satellite is rotating in orbit, and that orbit we can call it as the geostationary orbit, and the satellite which is rotating in that geostationary orbit is called, that is a geostationary satellite or parking satellite. And this orbit is also known as a parking orbit. And what are the conditions to be obeyed by this geostationary satellite? Here the time periods of self-revolution of Earth, and the time period of that satellite around the Earth, they have to be same. So that's why time periods for the Earth and again the time period for the satellite are same. But here the time period has different meanings in both cases. In this case it is a self-revolutional time period for the Earth, and for the satellite it is the revolution around the Earth. If these two time periods are same, then automatically now everywhere, suppose if you are taking, this is the satellite is somewhere here like this, then the line joining will be here. And suppose if the satellite, this point in some particular interval of time, this point on the surface of the Earth is coming to this position, then automatically here this geostationary satellite also will come to this position, because already their time periods are same. That's why here when you are coming to the velocities of that Earth and again that geostationary satellite, in these two cases the velocities are, angular velocity of both of them are same. Angular velocities are same. This is the d theta. Here the angle covered by this particle and angle covered by this satellite in that particular interval of time is same. That's why angular quantities are same. Angular quantities means that is the angular velocity, and again the angular displacement, angular accelerations, all these are same. But when you are coming to the linear quantities, that linear velocity is more for the GSS when compared to the linear velocity of Earth. Linear velocity is more for that GSS, so it will be around 3.1 kilometers per second. That is the linear velocity of that GSS. And the next point is here the position of that GSS, the height of that GSS from surface of Earth is, it is around 36,000 kilometers. And here from the center of the Earth it should be 36,000 kilometers plus 6,400 kilometers, so that it will be, that is 42,400 kilometers from the center of Earth, like this. So now this is the information about that GSS. Once again I tell you, here first of all, when if the time periods of Earth and again that satellite are same, and time periods here you have to understand what is the time period meaning in both cases. Here the time period means it is a self-revolution time period of the Earth, and here for the satellite means it is a time period around the Earth. So that's why if these two are same, that's why it is taking 24 hours. Already we know this is also taking the 24 hours. Then only that orbit is said to be geostationary orbit, and again that satellite is called the geostationary satellite. And here the angular velocities of GSS and again Earth both are same. Angular velocity is only same, but not the linear velocity. Linear velocity of that GSS is more, and GSS is the best satellite for telecommunications, because the basic purpose of that sending a satellite is telecommunications only, and this is the best satellite for telecommunications. So now GSS, the topic is completed. Now we are coming to that very important thing, is that is a gravitational potential. So after understanding a gravitational potential and a gravitational potential energy, then only we can come to that escape velocity. So after understanding the concepts of gravitational potential and the sign convention what we are giving while you are taking that gravitational potential, and after that gravitational potential difference and potential energy. Now gravitational potential, and that is indicated by V. So gravitational potential that is indicated by V, in this case it is the work done in moving a unit positive charge. It is the work done in moving a unit mass in this case. So unit mass in this case. So that's why what we are taking, it is the unit mass means 1. That may be 1 kg or 1 gram. So that is unit mass is taken, and that is to be brought from infinity. It is the work done in bringing unit mass from infinity to a point in the gravitational field. To a point in that gravitational field. Suppose we are considering this the point, to a, which is at a distance of small r. So to a point in that gravitational field. So that is known to be the gravitational potential at that point. Because the gravitational potential at that point means that depends on the distance. So that's why whenever that distance is changing, potential also has to change. So that's why you have to indicate it is a gravitational potential at that point. So once again I tell you, here it is the work done in moving or in bringing a unit mass from infinity to a point. To a point in a gravitational field. To a point in a gravitational field is called the gravitational potential at that point. And the same concepts we can understand even in case of that electrostatics. There you call it is the electrostatic potential, and in that case you are bringing that unit positive charge from infinity to a point. And the same that can be discussed, that is in magnetism also. So like that, now here it is gravitational potential is there. So in this gravitational potential, which is that unit mass is to be brought from infinity to this point P. And for that we are taking some elements dx is taken. Some element dx is taken, and first of all we have to find out what is the work done. What is the work done in moving that unit mass through this elementary distance dx. We have to find out that work done in moving that unit mass through this elementary distance dx. We have to find out that first. So here we are going to prove this formula, V is equal to minus gm by r. So this is the formula that you have to prove, that is a gravitational potential. So first of all we have to understand the sign convention here. So in getting this work done, because here it is algebraic scalar, gravitational potential is algebraic scalar. Its meaning is we have to give the sign convention. It is not a vector quantity, but it is algebraic scalar. So here in this case, what the sign convention that we have to give? Here work done by the, while it is coming from this infinity to the point P, work done by that external agency. Work done by that external agency is always considered to be positive. Work done by that external agency is always considered to be positive. And work done by the field, that is considered to be negative. So that's why once again I tell you the sign convention here. So because the same sign convention comes in electrostatics also. Here work done by the work done by that external agency in bringing this positive unit mass to this point P. So work done by that external agency is taken positive. Next, work done by that field on that unit mass is taken as a negative. So we have to apply that sign convention. We have to understand that sign convention also. Now here what is the distance, what is that work done while you are taking that unit mass through this elementary distance dx. So first of all we have to find it, and after that only we have to integrate, applying that limits to find out the total work done in bringing that unit mass from infinity to the point P. Why we are applying that integration here, I tell you now. So first of all we are finding that work done by the field. It is work done by the field because this mass is attracting that unit mass. This mass m is attracting this unit mass. So that's why it is dw is equal to, it is the f, and thereafter it is dx is also there, and it is cos 0, f dx cos 0. So that's why it is f dx only, and in place of that f we can apply that it is gm by capital G and small m by, and here that distance is dx we are considering it is at a distance x. So here that is f is equal to gm by x square, that is the force of attraction. It is the force that is existing at this elementary distance. G m1 m2 by d square. Capital G, m1 is a small m, m2 is unit mass, and d square is this x square is here, gm by x square. And here that dx is also the distance, dx is here like this. So once I tell you, so first of all, already we know the definition of gravitational potential. It is the work done in bringing a unit mass from infinity to the point P, which is at a distance now here to the point P in the gravitational field. So in that case, first of all, we have to understand that sign convention. Here the sign convention is work done by the external agency is always taken positive. Work done by the field is taken as a negative. So in this case, dw is equal to, that is here f dx cos 0, because here in this case, here in this while it is being brought to this from infinity to this point P, the work done by the field is f dx cos 0. Why it is cos 0? Because here the field, this mass is attracting, and that unit mass is also moving like this. That unit mass is also moving like this. Force and displacement are coinciding. That's why cos 0 is coming. Force and displacement is coinciding. That's why that is a cos 0 is coming. Now f dx cos 0 and gm by x square dx is here, and we want to find out the total work done in moving that unit mass from infinity to the point P, and for that you have to apply integration. Here why we have to apply that integration? Because the force is not at all constant here. Here the force is not constant here. So here it is some force, and here it will be another force, here it will be another force, here it will be another force. So that's why that force is continuously changing. If at all the force is constant, you need not apply any integration. It is simply the product of the force and displacement. But here the force is not constant. Then to find out that total work done, you have to apply that integration in between the limits. Integral dw is here, and integral gm by x square is there, and again the dx, and the limits are, you are bringing that unit mass from infinity to the point P. So that's why infinity becomes a lower limit, and that to that point P means r will be that higher limit. R will be that higher limit. Integral dw means it is w. Integral dw means w, because here we are applying that integration formula, that is integral dx is equal to x is the first formula we are applying, and the second formula that we have to apply, integral x to the power n dx is equal to x to the power n plus 1 by n plus 1. X to the power n plus 1 by n plus 1. So that's why integral dw is equal to w, and gm is there, it is a constant, and thereafter it can be taken integral x to the power minus 2 dx is there, and infinity to small r is there, and gm is there, and thereafter x to the power minus 2 plus 1 according to that formula, x to the power minus 2 plus 1 by minus 2 plus 1, and as usual we are giving that limits infinity to small r, and that becomes, it is a minus gm, and it is a 1 by x is there, and thereafter infinity to small r. Now we have to apply these limits, and is equal to minus gm is here, and thereafter it is a 1 by r minus 1 by infinity is here, and that becomes a minus gm by r is there. It is a minus gm by r is here. So that's why the work done in bringing that unit mass from infinity to the point P, according to the definition, it is nothing but a gravitational potential. So that's why according to the definition of the gravitational potential, that work done is equivalent to V. V is equal to minus gm by r is there. So that's why this formula is minus gm by r. Here, as I already told you, here this work done is nothing but it is the work done by the field. That's why the minus is coming. It is a work done by the field, that's why the minus is coming. Suppose if at all the work done by the external agency, this should be plus. Now here it is work done by the field, that's why minus gm by r is there. And this is the maximum value of that gravitational potential will be, that is possible at infinity, and it is 0, because r becomes infinity and it is 0, because when the unit mass is at infinity, it has the maximum gravitational potential. It will be, should be equal to 0, and when that mass is being taken from infinity to this point P, as it is approaching this point, then gravitational potential is decreasing. It is decreasing. So its maximum value is the 0, and thereafter it is decreasing. So always, except at the infinity, always gravitational potential is negative. always the gravitational potential is negative. So this is so far we could complete in this class, that is where we have started, that is the Keplars laws. So first Kepler as far as that astronomy is concerned, that is the planetary motion is concerned, that is the Kepler's laws, and for that Kepler's laws we have the two formulae, and thereafter it is the orbital velocity, that is also over, and it is a gravitational potential, and I gave the definition of the gravitational potential and the sign convention for that, and thereafter we derive the gravitational potential while you are bringing that unit mass to this point P, V is equal to minus gm by r. We will continue in the next class. Thank you.